The broadcast is now starting. All attendees are in listen-only mode.
Welcome to another Directions Mag Geospatial webinar, today sponsored by Esri. I'm Barbara Duke, Managing Editor here at Directions Mag, joined by my assistant webinar producer, Lynette Qualia. If you have any questions about your connection, just drop us a note in the chat. We encourage you to read our new feature articles tomorrow, daily news, and view more geospatial webinars, all at directionsmag.com. We're standing by to take your questions throughout the webinar. Just type those in the question box at any time. We'll answer as many questions as we can during the end section of the webinar, but we'll be collecting those and sharing those with the fine folks over at Esri. They'll follow up with you otherwise. We are recording today's webinar, and you can look for that recording as well as resources in your inbox following our event. Also, if you see something you like on the screen, there's a little camera icon. You can snap a pic as you go. Today, we are excited to learn more about deep learning. We want to welcome back Lorraine Tai and Vinay Viswambaran and David Yu. We're looking forward to seeing how this tool fits into the ArcGIS workflows. Welcome, everyone. Great to have you with us today, and I know we have a lot of folks excited about this topic.
Thank you, Barbara. Okay, so thank you. Vinay, David, and I are going to be going through the deep learning tools that we have here at ArcGIS. And I want to thank everybody who filled out their survey when they were registering. And this is a snapshot of what folks wanted to see. So we saw a high percentage, 31% wanted deep learning in ArcGIS, so information about that. That was followed by the workflows, so workflows and demos. So I'm happy to say that throughout this presentation, both Vinay and David will be providing some workflows as well as demonstrations so that you get an idea of some of the basics with deep learning in ArcGIS, as well as some tips and tricks and how applying deep learning to your analysis improves the time to which you can get to answers. So I'm going to hand it over to Vinay, who's going to start to take us through the basics and then some demos with deep learning. Take it away, Vinay.
Thanks, Lorraine. Morning, everyone. I'm Vinay Viswambaran. I'm a product manager at Esri. My focus here is primarily imagery and remote sensing. The scope of AI is constantly changing over time. You can see how these three items, AI, machine learning, and deep learning, are essentially linked subsets of each other. AI is when a computer does a task with some level of human intelligence. Machine learning involves techniques that learn from data, and deep learning loosely resembles the human brain. Now, there are a lot of technologies and tools that blur in here. There are several use cases of AI. There are several toolkits for enabling machine learning and different sets of algorithms that implement deep learning. Thank you. Now, from a deep learning perspective, here are 4 key imagery tasks that analysts and users really care about. There's pixel classification. An example for this would be land cover classification. Next is object detection. Typical examples would be detecting cars, planes, trees, and other objects in the imagery. Next is instance segmentation to get precise polygonal boundaries of each object. Building footprints delineation, for example, is an example. Objects, building footprints, building delineation are different examples that we've talked about so far. Lastly, image classification or feature classification, for instance, classifying a house or as damaged or not is an example of image classification. A quick overview of deep learning with imagery in ArcGIS. ArcGIS supports end-to-end deep learning workflows. We have a variety of tools in our ecosystem that enables this. So we have tools for labeling, training samples, preparing data to train models. You can train models within ArcGIS, and you can run inferencing as well. We support the key imagery deep learning categories that we just talked about in the previous slide. All of these tools are accessible through all of our clients. through all of our clients. The flagship desktop product, which is ArcGIS Pro, our map viewer, and ArcGIS notebooks or Jupyter notebooks. Now, this processing can be done using desktop or leveraging enterprise and running this at scale using ArcGIS Image Server. Now, here is an end-to-end deep learning workflow within ArcGIS. We can break it down into 4 key steps. First is collecting samples, collecting training samples. Next, export training samples. We have a set of tools to export training samples as image chips and meta information so that you can make it available for training models. Next is training your deep learning model. Currently, you can train your deep learning model using ArcGIS notebooks or Jupyter notebooks. Lastly, performing inference. You can perform inference, detect objects, or classify pixels using tools currently within ArcGIS Pro or leveraging enterprise to scale out your processing. At a higher level, here's the deep learning workflow. In addition to the deep learning pieces that I just showed you, ArcGIS enables efficient image management. You can manage large volumes of imagery using image services. You can then do advanced analysis on the deep learning results. These results can then be used in field mobility applications and monitoring applications such as ArcGIS workflows, ArcGIS operations dashboard, and so on and so forth. Next, a quick demonstration to show you everything that I've talked about so far. Scenario is we essentially need to use deep learning to understand, visualize, quantify trends or drilling activity at a basin level. So you're looking at the Delaware Basin and you can see the rapid growth of oil and gas development in this area. At approximately 10-meter resolution, we can clearly see the well pads across the landscape. Sentinel's imagery is great for change detection given that the refresh rate is once every 5 days. Now, when I compare the 2 images just over a month, you can see the number of well pads that have emerged and construction that has emerged over the different areas. Zooming out, here's our AOI that needs to be processed. I've got a large area to monitor, and this can be challenging, especially considering the rate at which the development is booming. We can solve this using deep learning. Step 1 is capturing training samples, as I talked about earlier. Next, we have a series of tools which will enable you to do this kind of processing. So first, the export training data for deep learning tool. You can specify input raster, specify a folder where you can define your output chips, define your input training sample, input training feature, and the output is a set of image chips with metadata which can be used for training your model. And this is what the chips would look like. Next, as I mentioned, you can head back into ArcGIS notebooks. This is ArcGIS notebooks. The labeled sample that we've extracted in Pro is now being consumed within this notebook. The Python API includes a variety of tools for data preparation, tools for model training, and complementary tools to simplify the training process. This makes it easy to train a model accurately. Once done, we can save this model, which can then be accessible across the organization. Using additional tools, you can then do inferencing, in this case, object detection. And here are the results. Now, what we've done in this case is I've done object detection on 12 different slices of imagery over the year. Now I can step through time and see how the well pads have emerged. So here we have it. We found 1,300 new well pads since Jan of 2018. Using these results, we can visualize emerging patterns over this area with regards to space and time. You can immediately see the patterns and regions, cold regions and hot regions indicating increasing activity. Next is using my deep learning results. I can review neighborhood fracking activity that could impact my operations. Zooming in around, I can check activity around my lease. This gives me a dynamic representation of well pad count and the type of different assets that I have. And we can also filter based on specific time periods, or simply pick a slice in time to visualize assets that were developed into that time period. All right, for those of you who don't know, ArcGIS for Python has rich functionality. On the right, you're seeing the different capabilities of this API, but they're really the modules that are available. They let you do things like feature and raster analysis, network analysis, schematics, and more importantly, what we've newly added is the ArcGIS Learn module. Using this, you can train your deep learning models. In addition to training, there are a variety of applications that you can go through. So this is the same workflow that you just saw, training using the ArcGIS API for Python. How we've made it different. Previously, you were mandated to install external deep learning frameworks. You had to write dozens of lines of code, which eventually translated to hard processing to actually derive a trained model. Now, with the ArcGIS Learn module that is available as part of the ArcGIS API for Python, you have no installation. It's just available as part of ArcGIS notebooks. In addition to that, like I just showed you earlier on, it's just 3 to 5 lines of coding. We've simplified the whole process of data modeling, of training your deep learning models. Now, I'll go over another example, another end-to-end workflow, this time highlighting notebooks a bit more. The scenario in this case is the Woolsey fires in California that occurred late last year. Here is our area of interest. And here are approximately 10,000 buildings that need to be classified. Step 1 is capturing training samples and creating image chips. So these are essentially the training samples that we've captured. Again, just like I'd shown you in the previous example, we've created a bunch of image chips using the export training tool. Now switching back to ArcGIS notebooks, we can go through the process step by step. Firstly, using the prepare data method, you can augment your data. These are all of the chips that have been exported through ArcGIS Pro. You can augment the data and then use that for model training purposes. There are a series of tools that we provide to complement training and create an accurately trained model. Users can essentially visualize the learning rate of the model with comparative loss. We train it over 10 epochs, and you can see the model converging to 99% accuracy. Now, comparing the ground truth predictions versus the input training samples, you can see the results are pretty accurate. Lastly, you can deploy the model, define the damaged buildings, and this can be done on enterprise, or you can run the inferencing locally using ArcGIS Pro. Here are the results. Here's just one of the examples. I've zoomed into one of the areas. Zooming out to the extent, these are about 10,000 different buildings that have been classified as damaged and undamaged. What we've then done is we've taken the process, we've taken the results into Network Analyst, used that as barriers and identified shelters that are within a 20-minute walk time for anyone who's been affected. And lastly, I pull this into dashboards to get a better understanding of the number of damaged buildings for any given area of interest. You can see the total damaged building value and the average block population for any given area. This is a dynamic representation of the data. So that was an end-to-end workflow. And clearly what you could see there is deep learning is an integral component of these kinds of imagery workflows. But what ArcGIS really brings is the spatial component. You can see the real value that ArcGIS is bringing when you add the spatial context into your workflows. So in addition to those two workflows, we've done deep learning on a variety of different applications, all the way from assessing damaged structures, delineating building footprints, land cover classification, road delineation, identifying road cracks, so on and so forth, all of it which is listed in here. There are many more examples which we've done. And now I'm going to hand it over to David, who's going to cover a few more interesting applications.
Thanks, Vinay. So first, a little bit about myself. My name is David Yu. I'm a data scientist for the GeoAI team here at Esri. I work very frequently with raster data in order to come up with interesting and hopefully compelling machine learning solutions to various GIS-related business problems. And I'm here to share with you a few of these projects and how they were built inside the ArcGIS ecosystem. So up to this point, we've talked through 2 end-to-end deep learning projects involving raster data. As you can imagine, there's a bunch of more fascinating problems that we were able to tackle with machine learning that we don't have the time to go into details about, but which I can give a brief overview. And keep in mind that these projects are not necessarily based on raster data, but also vector and streaming data. And some of these projects are, of course, more experimental than others, but by and large, these are all the things you can do today leveraging ArcGIS components. So just to give you an idea of the breadth of these projects, let me quickly walk through the 6 panels that you see on the screen here. First off, we have the object detection from imagery, which we use to evaluate parking lot occupancy and also track parking behavior over time. Next, we have object tracking and tracing from drone video feeds, which we've used to understand vehicle behavior and determine whether vehicles are stationary, parked, or speeding. We then have object detection from videos, specifically live CCTV feeds, from which we are able to extract real-time insights for enabling traffic pattern analysis and anomaly detection workflows. We've used gradient boosting methods to perform accidents prediction based on spatial temporal factors and also weather patterns in Utah. We've used historical origin destination data to accurately predict the arrival times of vehicles in California and Nevada. And finally, here we have applied machine learning to GPS breadcrumbs data from oil companies to automatically detect emerging road segments. So those are more of a high-level overview of these projects. Let me now dive a little bit deeper into a specific project, 3D building reconstruction with LiDAR and deep learning. So one problem we've seen in the building assessment and city planning space is that mapping out and constructing 3D models of structures tend to be pretty labor-intensive, very time-consuming. And this would often involve designers sitting down and manually creating digital renderings of buildings using CAD tools. Now, this process has been made considerably easier for city planning using procedural generation within City Engine using CGA rules, but the task of modeling existing cities remain a pretty intractable problem because you're not only having to understand how tall structures are, but also their footprint geometry, their roof types, and for surveying workflows, analysts often have to do this across a very large extent. So typically what happens is an aerial LiDAR point cloud of a region of interest, or AOI, gets transformed into a digital surface model. An analyst goes in and manually picks out buildings and structures and digitizes the roof according to its type. And afterward, a set of procedural rules are applied to extrude the buildings into a 3D scene. But this task of manual digitization usually forms the most time-consuming step. And this is the main headache we wanted to address going into this project. But fortunately, modern AI techniques are advanced enough to fully automate this process from aerial LiDAR imagery. With this project, we teamed up with Miami-Dade County and also NVIDIA to see if we can create an end-to-end machine learning workflow. And by end-to-end, I mean we want automation to happen from when LiDAR is first received all the way to getting a full 3D reconstruction of the AOI in anywhere from hours to minutes. And what this allows for is resources to be placed on refinement or other critical post-processing step and away from having to manually draw out polygons over roofs. Before we get into the automation process though, let me talk through a little bit about what the training step looks like. So we trained a model on about 200 square miles of aerial LiDAR. We went in and manually digitized about 200,000 roof segments in one of the following 6 categories that you see on the screen here. So we have gable, hip, shed, mansard, vault, and dome. And what happens at inference time is the model takes in a single band rasterized LiDAR and spits out a feature layer consisting of building footprint polygons that are categorized into one of these classes. We also wrote a script that ingests this output and automatically draws up a 3D scene that lends itself for further analysis or can be shared in an online viewer. And so the automated workflow can really be divided into 3 parts. And you'll see some of these parts of the process start to echo the principal steps to running a machine learning model that Vinay has just mentioned. The first step is data collection and labeling. So this clip here shows Miami-Dade County with a grayscale raster representing aerial LiDAR data and some manually digitized building segments with a discrete coloring scheme representing the 6 roof types that we just talked about. And as you can see, as the map pans around here, we see although the main buildings have been manually digitized, a majority of the smaller ones are still missing. And this is okay because we went ahead and ran the expert training data for deep learning tool and shipped out those images into a training set. These were fed into a machine learning model called MaskRCNN, which leads to this very nice inference result, which is the generated building footprints. As we see, in spite of the incompleteness of the training set, the model was able to produce a polygon mask over every building in this extent that we passed in. And not only that, it's able to correctly classify the roof type of these buildings, attach a square footage, and also estimated floor count. So when we turn off the base imagery layer, we can fully appreciate how these results look. We can also toggle between the original training set and the inferred output to see how many more structures have been added. And the final step here is 3D reconstruction and post-processing. So this video shows a fly-through of a few blocks of 3D buildings which were detected and accurately restored out of aerial LiDAR data. There's been no manual modification to these building geometries whatsoever, and the only post-processing we ran on top of these results was the regularized building footprint geoprocessing tool and a couple of procedural generation rules. So all in all, some very beautiful results that you see here. Now let me quickly switch gears and talk about another exciting project we've done here, high resolution land cover mapping. So unlike object detection, this is more of an image segmentation problem, and that means associating class labels to rasters at a pixel-wise level. The image you see here is an example of a classified land cover map. I don't have the legend brought up here, but you can see that these red patches, for instance, represent building structures. Blue represents bodies of water, green represents wooded areas, and so on. To those of you who are unfamiliar with land cover mapping, it's a very powerful way of annotating data, especially if you're interested in monitoring ecosystem changes, if you're interested in, say, predicting NDVI indices, understanding hydrological processes, or even identifying illegal construction through change detection. So this being a repeatable decision-making problem of having to associate class labels to pixels at scale makes it fall into the category of problems that are really optimized for AI. And to give you an example of the opportunity cost of not using a machine learning-driven solution, we have the example of the Chesapeake Bay. To those who don't know, the Chesapeake Bay is the largest estuary in the United States with about 18 million people living in the watershed. And the Chesapeake Conservancy is a nonprofit dedicated to conserving the landscapes and rivers and restoring the region's natural resources. And to do so effectively, it actually had to manually create a land cover map that classified land use type from aerial imagery. And the result is a 1 meter ground resolution land cover set for about 100,000 square miles of land. And this is needed if you want to carry out precision conservation. But unfortunately, it took 18 months to process, which meant by the time the map was completed in December 2016, it was already out of date. However, thanks to Chesapeake's carefully constructed original land cover map, this is the first time that there's this incredibly rich, high-resolution data source that can be used to train a computer vision algorithm that would learn how to automatically classify land types from map imagery. We created our model on the GeoAI data science virtual machine, which is an Azure offering that ties together a bunch of useful ArcGIS capabilities to Microsoft's existing data science virtual machine platform. For training, we used half of the total Chesapeake's 100,000 square miles of data. And the training model, by the way, is a UNet model, in case you're wondering. And the other half of the images we use for testing. So when we ran the test images, we found that our model could correctly classify land about 91% of the time. But most importantly, this was 16 times faster than Chesapeake's previous effort. It took us about 150 hours to run the model versus the 2,500 manual hours that Chesapeake had to put in. And as a result, you see these beautifully labeled images. If you look closely at some of these images, you actually find the model was not only able to pick out forested regions from fields, but also the individual houses, like buildings. And even if you look closely, the model was able to pick out swimming pools in people's backyards, which is pretty surprising. So you may be wondering whether it's possible to have the same end-to-end workflow carried out in ArcGIS notebooks, and the answer is yes. So now let me quickly switch over to a notebook that I have pulled up here. So the first thing we want to do is connect to our GIS instance, and so this would allow us access to layers and models that we push to the portal. Here we're accessing our labeled data as training data, and this is what the labeled data looks like. For our base layer, we are getting NAPE imagery at 1 meter ground resolution for the whole of the United States. We're also creating a raster store where these images will be stored once they're chipped out. And to run export training data, it's literally one line of code here. And in the function parameters, we see the exact same settings we would enter if we were using the GUI tool. To train the model, it's equally straightforward. We first fetch our newly exported training data and run the prepared data function. And this automatically applies a series of random affine transformations to the images and labels and inflates the amount of training data by several factors. And so these are the augmented image that we got from running that function. We load a UNet classifier, which is part of the ArcGIS.learn module. We find the optimal learning rate, and we fit the model against our data set. Again, we see the straightforwardness of the Python API at work, where it's literally one line of code to perform model training. And when we show our results, we see our model output looks surprisingly well compared against the ground truth labels. So the left column here is the ground truth, and the right column is what the model predicted. So fairly good results. We can then push the model onto a portal where it can be viewed, accessed by other members of your organization. So there's no sticky handoff period where you have to walk through your colleague on the specifics of your implementation. Everything has been standardized in a way to extract out the complexity of running a model without compromising on flexibility. And for inference, we run the model over a large extent using classified pixels. Again, a single line of code, and the results are again pushed back out to the portal.
Thanks, David. So let's get to know folks just a little better and look at what industry you're working in. I know this is part of what you answered at registration, but this is a little more specific. Is it government, forestry, oil and gas, defense, utilities? And if it doesn't meet one of those, then feel free to drop in your industry into the chat, and we'll collect that there. Give folks just a second. Certainly an overwhelming winner on our list here. In first place, government, and in a tiny, narrow second place, down in utilities. So thanks, folks. We appreciate you sharing that. And oh, look at all these wonderful industries they're sharing via chat. Thanks, folks. We'll share that with the team. All right, David, back to you for a few more.
Thanks. So we talked about inferencing at a relatively smaller scale, but however, if your workflow requires that inferencing be performed on an even larger scale, say at the level of a city, a county, or a state, it can be very advantageous to do this using distributed raster analytics. So it's a mostly transparent process to the user, but under the hood, you can spin up raster analysis servers with GPUs to help speed up what otherwise might be a pretty long-running process. And to give you an idea of the speed up achievable through distributed raster analytics, we ran a building footprint model that looks like this over 60,000 buildings. With ArcGIS Pro, it took about 4.5 hours on a GP100 GPU, so that's a fairly good GPU. But however, with raster analysis servers, we're using 4 nodes, and it took a mere 20 minutes to run. So the general rule of thumb here is that if you're in a prototype workflow, or if your AOI is fairly small, it's a bit overkill to utilize image server capabilities. However, if you're thinking about bringing your workflow to a more production level, or if you need to perform, say, analysis over a large extent, using distributed raster analytics really is the best way to go. Okay, so seeing we still have a little bit of time left, I'd like to take this opportunity to walk you through a few more interesting projects we were able to put together. So the first clip you see here is about occupancy assessment from drone imagery. What you see here is the Esri campus parking lot, compiled and exported as an imagery layer from drone to map. We use an object detection model to not only come up with the bounding boxes that you saw earlier, but also classify the detected cars into distinct types such as pickups, SUVs, and sedans. We also imported an existing polygon feature layer of the parking lot, so we can very quickly and very accurately assess the current occupancy level, as well as toggle between different timestamps to understand the behavior of parking over time. You can imagine it's very easy to extract high quality consumer data from drone feeds such as this, rather than analyzing point of sale data, which can sometimes contain missing or invalid records or might otherwise be difficult to obtain. And this example here is an operations dashboard showing a live, publicly available traffic camera in Jackson Hole, Wyoming. Obviously, this clip is just playing on a loop here, but we've hooked up this CCTV feed to a dashboard where a model is able to assess in real time how many cars are moving across the intersection, how many people, how many trucks at any given time. And all of this is counted and aggregated in this dashboard. So this is obviously really useful for a particular road network, but you could also expand this out to a citywide scale and include a bunch of roadways or a bunch of intersections. And you may be thinking, great, this looks really neat, but wonder what the point of this is and why anyone would want to do this. So what you can do with this data is, if you have an idea of what's going on your road network at any given time, you can start to develop some normalized thresholds about each and every intersection, typically on a day-to-day basis. And having that baseline would be super helpful in formalizing an anomaly detection workflow, where every time a baseline is exceeded, those types of activities can be thrown on a dashboard, so you start to gather a sense of what anomalies are happening in that AOI and why it's happening in that area. Another great example that follows the same thought process of behavior analysis from detection is our tracking workflow. We come across a lot of these videos for various use cases where we're constantly looking for different means of insight extraction. And for the previous example, we saw that being built around car counting. Well, in this case, we actually want to analyze and trace out the paths taken by individual vehicles and see if we couldn't derive some insight from analyzing these driving patterns. And to do this, we started out with something simple. We applied a real-time object detection model to a drone video. This happens to be a model called YOLO V3, in case you were wondering. We expanded out this workflow by adding an algorithm called SORT. So this stands for Simple Online Real-Time Tracking. And so, as you may have noticed, now we have attached unique identifiers to each and every vehicle. And as these vehicles drive around, they maintain their tags in spite of the movement and orientation changes. We've also thrown in a custom distance measure to account for the anomalies over vehicle paths, and drew up a polygon geofence layer and literally gathered a bunch of co-workers to go down to a local parking lot to start driving around like crazy. And the results turned out pretty well. We're able to not only distinguish between cars that are on the lots versus cars that are stopped and outside of the lots, but also pick up any anomalous behavior, such as vehicles that are speeding, or vehicles that are parking, or any vehicles that experience sudden velocity changes. Here's an example from running some models over vector data. We use gradient boosting methods to perform accidents prediction in Salt Lake City. And we did this based on a bunch of characteristics such as road curvature, speed limit, proximity to intersections, hour of the day of the week, and so on. The colored segments that you see here on the video that are about to come up are accident predictions, so with red being highly likely. And the red dots that you see placed around the screen are accidents that did happen, and they're gathered from a data set that the model hasn't learned on. So overall, this model performed very well and was in fact able to generate some very useful insights that we as humans didn't even take into account. For instance, the model would attribute a slightly higher accident probability to roads going in a westerly or easterly direction at early times in the morning or late in the afternoon, whereas we certainly hadn't thought of the effect of sun glare during the data exploration phase of this project. In this particular example, we're using historical origin and destination data to accurately predict the arrival times of vehicles for a given point in space. This is a project we did, again, in collaboration with NVIDIA, where we simulated about 320 million sets of journeys. And by journeys, I mean just records consisting of origin, destination points, and the associated travel times. And we did the data collection for the region of California and Nevada. We then used an artificial neural network to predict travel times on a transportation graph. And here's the result that we got. So this is a clip of a set of 25-minute ISO contours and how they change over a 24-hour period. And each ISO contour simply indicates how far you can drive in a 25-minute window. And you see how these ISO contours shrink during business hours and how they expand back out during the night. You can also follow these ISO contours and see how they become more sensitive to changes due to the existence of roads and how they tend to become more robust to rush hour traffic where highways aren't readily accessible, say. And here is an example where we combined machine learning to automatically detect emerging road segments in well-pad construction sites. This is particularly useful in cases where roads are naturally formed and not planned out, like where new region undergoes development. We track the formation of these roads using GPS breadcrumbs from construction vehicles and ran a genetic algorithm over these points. So these results are then added to a digitized road network without the need for the human digitization process and without the need for any human analysis. It's fairly cool. And that's all I have. So I know that was a lot of material to cover, so hopefully you found some of these content interesting and instructive to how you might want to adapt a machine learning solution to your problem domain. And I will now hand it back over to Vinay for some concluding remarks.
Thanks, David. So we covered a lot of examples, end-to-end workflows where deep learning was an integral component. But clearly, most of the workflows, or rather none of the workflows, are possible, or you can't create information products that without using ArcGIS, without using the ArcGIS ecosystem. So all the way from managing imagery, this is done using the Mosaic dataset or image services, labeling data, data preparation, training a model, detect objects, all of these tools are available within ArcGIS. But to really create information products, once you have the results, you can run it through our analysis tools or analysis extensions, such as performing spatial analysis or leveraging network analyst to derive information products. And once you have those results, you can drive those results, or you can then monitor them or visualize them or quantify those results using monitoring applications or leverage those results in field mobility applications such as workforce. What's next? What's coming in ArcGIS for deep learning next? We're going to provide out-of-the-box deep learning models. So we're going to provide our users the ability to directly download deep learning packages, which essentially is a data model which you can then download into your machine, or you can work directly off of enterprise, run the inferencing and derive projects or derive products. So in this case, you really don't have to do the training process, model training, or capturing training samples. In addition to that, we showed you training using notebooks. This training is going to be brought into ArcGIS Pro. So geoprocessing tools are going to be exposed, enabling users to perform model training within ArcGIS Pro application, within the ArcGIS Pro application. The ArcGIS Learn module, which we talked about quite a bit, we have several enhancements. We're going to add several backbones and several model architectures as well. A lot of questions have come through right through the past half an hour. regarding samples. So yes, we will be providing a collection of sample notebooks. We have already uploaded a collection of learn lessons. We'll be adding some more that are specific to deep learning workflows for imagery. And more importantly, we're going to enable you to work with multiple GPUs for training purposes and for running inferencing. And this is going to be possible both using desktop. So if you have multiple GPUs on your desktop, or you have multiple GPUs on individual machines that are connected to your enterprise, you can leverage each one of those GPUs via your enterprise.
Thanks, Vinay. So we would like to learn more about your software skill improvement activities. What are you doing to improve those skills? I know we've got a lot of folks here that are taking advantage of webinars. Maybe you're doing some research online training types of videos and lessons. Maybe you are the YouTube champion. Which one of those resonates with you? You can actually pick a couple of those that make most sense. All right. Fantastic. So a couple more seconds, folks, and it looks like first and second place go to webinars and online training lessons. And then coming in next, YouTube video, reading, just research online, looks like, and YouTube videos. So thanks, folks. We appreciate your input. It's always helpful to us. And back over to our wonderful team at Esri.
Thank you. And thank you for answering that question. It's important for us to understand how people like to learn, because we then create those types of webinars, online training, classes and whatnot to help folks improve their skills. So we're just about coming up to the question time. Vinay, myself, and Dave are going to be answering these questions. I'll be reading them off. Any that we do not get to, we will supply answers to those as a post email to the group. So I'm going to start looking at the questions. So one question, what geometry do you use for the training samples?
So if I understand correctly, I think the question is more on the lines of what features are being used for training samples. So currently you can use feature classes to capture training samples within ArcGIS. One of the workflows which we didn't run through is capturing of training samples. Using the training sample manager within ArcGIS Pro, you can digitize samples. The samples get saved out to feature classes. You can even crowdsource your training process by storing all of these samples within a feature service. And that's how really the geometry of the training samples are stored. It's either stored within a feature class or a feature service.
Thanks, Vinay. Could the presenters please discuss the license details that are required? Like, do you need image analyst or image server?
So we talked about two possibilities. One is you can do the processing using your desktop. The other one is doing the processing leveraging enterprise. A couple examples which David showed was he scaled out his processing using enterprise. Now, if you want to leverage a cluster of machines, if you want to leverage enterprise, you need image server. If you want to run all of your processing on ArcGIS Pro, which includes exporting training samples, moving forward, you're going to have the ability to train your models and inferencing, all leveraging desktop, you need the image analyst extension to work.
Thanks, Vinay. Okay, how many training samples have been collected? Is it an automated process to collect these training samples?
It varies depending on your project size and depending on the features that you're trying to collect. David has gone through a variety of applications. Each one of those applications, David, if you want to go through and you want to talk about the number of samples that you used for each one of you.
So really it depends on the problem space you're dealing with. So for instance, the car detection stuff that I showed earlier, for that we actually collected about just 400 images, and then we used image augmentation to be able to manually inflate out that data set. And of course, for a lot of these projects, you can first collect data from open source material, right? So for the car counting stuff, we can get cars overhead with context, that data set, or the Stanford open car data set. And in terms of the automation process for collecting data, that's also possible. So for instance, inside Pro, you can use the training samples manager to first create a small extent of labeled, say, tiles. And then we can run a bunch of tools within Pro. So there's actually an option to run a classification wizard that it's going to help you create a large data set based on the extent that you pass in. And that really can be used as a training set for a even bigger model that you're going to train against.
I'd like to add a little bit to that, given the power of ArcGIS, and this is one of the reasons where I said adding the ArcGIS ecosystem into the whole equation makes deep learning much more powerful. In a sense, the example where we talked about the building footprint delineation, we literally did not capture a single training sample. We just used building samples that was provided by the county, leverage that GIS data set directly within ArcGIS, use it in the context of the export training deep learning sample tool, provided an image, the output was a chip which we could use directly. So there was literally no training involved in that, creation of training samples that was involved in that.
Okay, great. So you can see there's a lot of different ways that you can collect your samples and also the number of training samples that are actually required. What was the LiDAR spec for the building reconstruction? Points per square inch. The LiDAR spec for the LiDAR example that you gave us?
Yeah, points per square inch.
Yeah.
I'm not too sure about that actually.
Okay, we'll find out that answer and we'll also get back to you guys on that. Next question, are these notebooks available from the Esri gallery?
So we have put out a few notebooks already. It's available on GitHub. I think we'll be sending it as part of resources. In addition to that, yes, as part of the Esri notebooks gallery, we will be adding some more notebooks as part of 10.8. Moving forward, 10.8.1 as well, we'll be adding a bunch of different notebooks which you can work with.
Next question. Where do I get the ArcGIS API for Python training model? Anyone that was presented?
Could you repeat that again, Lorraine? I think I didn't catch.
Okay. Where do I get the ArcGIS API for Python training model?
I think
Through the notebooks.
I think the information was, sorry, the question was more on the lines of where do you get information about the ArcGIS module? You could search for within the ArcGIS documentation website. If you search for ArcGIS Python module, it'll take you directly to a link, which gives you a lot of information about the ArcGIS API for Python. In addition to that, it gives you ArcGIS Learn. It gives you information about the ArcGIS.Learn module as well. And this will be one of the resources that we'll be sending you.
Okay, next question. Can I get any sample data or tutorials for all the case details that GEOI-AI is supporting?
We have some of the samples. We have 2 learn lessons currently, which we've put up. One is detecting palm trees, and the other one is detecting encroaching properties along pipelines. In addition to that, like I said, we're adding some more samples on GitHub. The sample where we talked about the damaged buildings, the damaged construction, those samples are made available through notebooks. So that gives you an indication of how to do the entire processing using Jupyter notebooks or ArcGIS notebooks.
Great. What is GeoAI?
So interesting question. So GeoAI stands for the intersection between GIS and artificial intelligence. So basically, It's about applying artificial intelligence to any sort of GIS-related business problems. So it's not a product. It's more like solutions, right? It's more like how do we apply the latest and greatest developments in machine learning to solve existing GIS problems.
Okay. Have you tried doing car counting on ortho imagery? It would be interesting to take our citywide ortho imagery, count the total cars for a period of time.
Yeah, it's funny. We did this for a smaller extent. Obviously, we can't talk about the client, but we were able to, count cars from ortho streaming data. But yeah, it's not a difficult workflow, right? So once you have those bounding boxes around the cars, really, it's super easy to be able to pull that into like a CSV somewhere and count the cars.
Okay, great. Let's see. I'm happy to be learning more about GeoAI. Is it also possible to execute some of these processes in ArcGIS Desktop?
Yes, in fact, all of these processes, we showed it in desktop and notebook.
Yeah, so we saw some of those notebook functions that both Vinay and I were pulling up, but the same functions actually exist within ArcGIS Pro. And you can run the same models as well.
Okay. Are the training data samples, for example, the 3D buildings that you talked about, also made available?
Unfortunately, no. So you'll have to collect your own data on that.
Oh, one of the questions coming up was, I'm new to AI and deep learning in ArcGIS. Is there any more information that could be made available for end users to get up to speed? And I can take this one. As part of the resources that we're going to be supplying to everybody who's been registered for this webinar, there are 2 deep learning training courses. So these are courses that provide you sample data and instructions to go through and how to actually perform some deep learning analysis. So that will be a great opportunity for the users to get their feet wet and start learning about that. What version is the deep learning module included in ArcGIS Desktop?
Could you repeat?
What version is the deep learning module included in ArcGIS Desktop? It's now.
Yeah. Yeah, it's available 10.161, right? Yeah, it's available as part of the ArcGIS API for Python 1.6.1. But then more specifically, if you're asking about the desktop and enterprise releases, it in Pro 2.4 is when we had introduced it, and Python notebooks came out, or ArcGIS notebooks with the ArcGIS module came out, I think 10.7, if I'm not mistaken.
Are there any GPU recommendations?
So really, it depends on the GPU memory, and it depends, of course, on how many batches you want to run the training with. So if you're running those tools inside Pro, actually, there's the option for you to be able to select the batch size. If you're running, say, detect objects using deep learning, you can specify that. So even if you have a GPU that doesn't have a lot of memory or doesn't have a lot of compute capability, you can still run those models, right? And of course, even if you don't have just that, you can still run this over on CPU, provided you have, the correct deep learning libraries installed. So inside the ArcGIS Pro environment, you can install TensorFlow, GPU, Keras, all of that, and yeah.
Okay, here's an interesting one. The user currently uses deep learning to automatically detect birds, especially birds on a lake. So they're asking if they can do that when they have images of birds with XY coordinates. Can they use deep learning to then detect them?
So you mean if you have, okay, so we had a similar scenario where we had a certain species of animals and we were given locations. We can use those locations directly as chips But in addition to that, you need an image of the bird as well, if that makes sense, because you're training the model, or you're training the system, you're training the framework to understand what a bird looks like. So just providing the XYZ will not be sufficient. You need to provide what a bird would look like. So you need the input images as well, not just a location.
Okay, I think we'll take one more question before we hand it over. Can I use Mosaic dataset in deep learning?
Yeah, so Mosaic datasets is our primary data model to manage large volumes of imagery, and that is what we recommend when you're working with large collections of imagery. You can step through individual collections. You can step through individual collections of imagery within a single Mosaic dataset, or you can treat a mosaic as a carpeted image and work with that as a whole, as a mosaic image, and work with that as a whole. The Mosaic dataset is basically served out as an image service, and then you connect to an image service directly. That's the optimum method to work with imagery within ArcGIS.
Okay, great. Okay, Barbara, we'll hand it over to you. There's still a few more questions, but like I said, we will get those answered and supplied to the team.
Wonderful. I know you guys will follow up with everybody. Lots of great questions, folks. So if you do have another burning question, don't hesitate to type that in here very, very quickly. So thanks again for attending today. Remember that we are recording and we will archive that for you. You'll get an email from us that has the link to the webinar. You'll also get a link to your certificate as well as resource links. We appreciate you completing the brief survey on the way out. And special thanks again to Lorraine, Vinay, and David for sharing their expertise. We hope you make it a great day and tell a friend about Esri and Directions Magazine. We'll see everybody later.